back. We're going to be dealing with a couple more issues chapter 4. Not a very long chapter. I think I may have mentioned in class already. We have a couple more things to do. We've only been looking so far at trying to find the midpoints of lines, and we did that briefly last week. We also have to deal with the concept of distances on the Cartesian plane. And now, of course, we know the presence of a third axis, the z-axis. And so we're going to have to work out how to find distances on three-dimensional 3 space. So like any 2 points in space, even if they're not at the same altitude or on the same plane. Well, what does that mean for us here? So I'm going to advance the slide here. And, okay, the heart of the matter is this. Distances... any distances, there's always a straight line that connects any 2 points. So as a result, we're going to end up using an adaptation of the Pythagorean theorem or Pythagoras' theorem. And just to recall that Pythagoras' theorem says that the length of the hypotenuse is equal to the sum of the squares of the 2 sides that sit perpendicular, that span it. And here's an illustration of just that very point. Common mistake is that people, if given any 2 numbers around a right angle triangle, they always assume that you add their squares. But that's not true if one of them given to you is already the hypotenuse. In those cases, you have to subtract back to find one of the missing lengths. Okay, so the longest side in a triangle of a right angle triangle is the hypotenuse, and then A and B are sometimes referred to as the legs or the other 2. Okay. Now, our goal is to transfer some of this known information about measurement over to the Cartesian plane because we deal in the realm of coordinates, and a lot of the information that we seek from Cartesian geometry on the XY plane will be driven by our knowledge of the coordinates of the location of the point, so like basically its address. So if I take a look at this one here, I think what I could, with some sort of reasonable accuracy, come up with estimates of the coordinates of those points. But how do I find the length of the line? I mean, some could say, well, just get out a ruler and measure it, but that's not really accurate. That's a bit juvenile, in fairness. So we're going to have to base this on more of a precise formula, because we are going to expect to have quite precise measurement or calculations, and a measurement just won't be able to do that. So what we do is we try and envision a right angled triangle surrounding that length that we want. In essence, we're going to turn in our mind that straight line on the Cartesian plane. We're going to think of it like a hypotenuse, because the right angles, therefore, that support it are going to be parallel to the axes, the x-axis and the y-axis, because that way we can get accurate measurements here by considering the coordinates. So what do we have here? We're going to assign some variables a, b, and c around that triangle. And I'm going to notice that in this case, based on what I'm looking at, I think that this value here is 3 and that value is 11. This one here is 6 and 2. So I came up with these values of 8 and 4 as the perpendicular lengths that support the hypotenuse. And then I went through a very normal calculation here with Pythagoras' theorem. The sum of the squares of the perpendicular sides are 64 and 16. They add to 80, so the square root of 80 is this long number here, which I've chosen to round off to be 8.94. Hence, I can say that that hypotenuse, or that line segment on the Cartesian plane, has a length of 8.94, which is far more precise than I ever could have come up with using a ruler or just estimating with my eyes. But as always, we're trying to make a formula out of this, and this formula is our formula kit for the course, and here it is right here. And these are familiar bits of input here, x2, x1, y2, and y1. It just means the x and y values of the first point and the x and y values of the second point, and we enter them in there. Now, I've got a way. Okay, the key idea, hope you find that amusing, depends on us knowing the coordinates of the end points. So what do we do? If the coordinates were in fact here 3, 2, and over here 11, 6, I would say I can take the difference between the 2 x values, and I'm going to take the difference between the 2 y values, and those values are embedded in the diagram. The difference between these two is 8, and the difference between these two is 4, and I could then put them in that formula which we recall from before. So this formula here, I don't have to think of it as a triangle. Even if I was just given the coordinates listed out, I could apply the formula just by using the numbers as input. Okay, so what does that mean? Let's go off and see what happens in 3D. Well, good news for everybody. The Pythagoras theorem is perfectly interchangeable into 3D. If you have a line, like here, let's just read this question. It says, a traffic camera is located at the point H, as diagrammed there to the right, on a tower. There's a tower there. There's a bridge, GE or EG, that crosses a river. And we're trying to find the length of the line that goes from G here to H here, or the other way around. It doesn't make any difference. Well, first, a little bit of a thought about the Pythagorean theorem. Now, obviously, a line in space that has not just x, y, but also a z is supported by three lines that are perpendicular here. There's this one down here, there's this one here, and then there's the height. And lo and behold, as it turns out, you simply add up the squares of the three mutually perpendicular lines, because this line is perpendicular to this one, which is perpendicular to this one. They're all perpendicular to each other. Hence, that's why I say mutually perpendicular. And I add their squares and take their squares, add them up, and take the square root. And it turns out this is exactly 19, because that one there is supported by all three of those numbers, 6, 10, and 15. Now, if I wanted to take the last formula and extend to 3D as well, that's fine. I just add the extra square, the difference between the two z coordinates. Now, and you can see that these points here, A and B, are expressed using three space coordinates. If I'm here, back in my diagram, trying to find the length of the line that connects H to G, that's this one here, all I need to do is know the coordinates at its endpoint, and they'll become the input values for my little formula. And here we go. Here's the formula. Here again, it's the difference between the x's, the difference between the y's, the difference between the z's, all squared, added, and then take the square root of that sum. So there's the coordinates at the endpoints. Here's the x's, the y's, and the z's. I find those differences, which are there, 10, 60, and 80 respectively, and I add their squares and take the square root of the sum, and that's 100.5. And that would be a measurement that's completely impossible to get, either by inspection visually with our eyes or measuring it some other way. It absolutely has to be a calculation to be accurate. And again, the key idea is to be using this formula, you need to know the coordinates of the endpoints of the line whose length you seek, and that's true in 3 space, 3D, or in 2 space, 2D. All right, let's take a look here. Applications. Skyways Airlines has policy that passengers cannot carry luggage. The diagonal measurement more than 56. So this line here, if you were to try to imagine getting the longest straight line possible inside your bag, it can't exceed 56 centimeters. So Katie's bag, here comes Katie very confidently walking through the hangar. Her bag is 40 by 30 by 25, and we want to know whether or not that length is going to be allowed or not. In this case, it's not really necessary to transfer these measurements over to Cartesian 3 space and try and make a diagram. This is just a cuboid, and a cuboid is nothing more than basically a box. And a suitcase in this context could be thought of as being like a box. So I'm just going to take the sum of the squares of its outer or mutually perpendicular dimensions, and the squares of 40, 30, and 25 add up to 3125, which happens to be the square approximately of 55.9. So it looks like Katie just made it under the wire. At 56 is the limit. Sounds like she just made it for carry-on. So yes, she can't carry that bag on. Okay, so now we're going to take a look at a pyramid. A pyramid has got a height of 40 and its square base edges are 50 long. You may have seen pyramids before. Hey, what's that up there in the upper corner? Those are pyramids for sure, and I think you actually know a couple of those people there. It was many years ago. So what do we have here? I made a little video to try and show you what this thing looks like, because I am going to switch this one over to Cartesian geometry, because that point D looks a little elusive to me, and I'm not sure how I'm going to access it. So I put the 4 points down that measured out the square base, and I'm highlighting them in that magenta, pink, purpley color. And then I'm going to put some of the diagonals up there. I'm going to change the color of the last one to something different here. Let's go with blue. So basically they're asking, can you find the length of that blue line based on the measurements that you have? Now, you'll notice that I have this point D elevated in the middle, and it's at a height of 40 meters above. So I'm going to try and come up with coordinates for the different points. Now I've selected to go with point A and point D. So what that means here is I'm going to have A is 50 in the X direction, 0 in the Y direction, and 0 in the Z. And since D is right above the middle, as I've diagrammed there, I'm going to drop a point right there, that means it's going to be 25 in the X, 25 in the Y, and of course, as advertised before, it's at a height of 40, hence the coordinates that we have here. This allows me to use the formula. The formula is the difference between the X's, the difference in the Y's, difference in the Z's. Take the squares of those differences, add them up, take the square root, and it's 53.4. So that's this length of the blue line. All right, let's continue on here. The other thing you could have, now I elected to go with a Cartesian 3-space model of this, but you could have tried to build a cuboid around this three-dimensional sort of hypotenuse, this line right here. And the way it would have looked is something like this. You need to be quite, you gotta have decent visualization skills to try to picture a cuboid around it whose outer measurements would be 20, 20, 25, 25, and 40. But that will also work and get the right answer of 53.4. Now, the last one is a bit of a visualization game here where we're trying to work out lengths in this, what looks kind of like a tent or a small shed or something like that. All right, so first we're going to try and find the distance between A and B. Now, A and B is here. They've already told us that one of the distances here, our lengths, is 4, and that's the height here. Now, the other one is, they told us this one is 8, half of which is here. Now, why do I want that? Because to access this one that I've labeled H, I'm going to have to use a triangle principle in there. And that means that height is going to be the difference of the squares of 5 and 4, because 5 is acting as the hypotenuse in this case. Therefore, 25 minus 16 is 9, and the height, therefore, is 3, which is obviously the square root of 9, meaning that the overall distance from A to B must be 7, because it was already 4 high, and we're adding this extra 3 to it, and we would get AB, the height is 7. If I wanted the distance from A to C, I'm going to try and picture where that is first, and then capture the relevant outside measurements. The height AB is one of them, already calculated to be 7 from previously. I track out their 4 in the front there, half of the 8, and then 12 on the way back, which I've just underlined. And I add up the squares of those numbers, and I get the square root of that sum is 14.5. B to E, try and track out where that is and visualize that. Of course, there's a right angle right there. So the height was 7, previously calculated, and that 6 is half of that depth all the way back, because E is in the middle. And so I add up the squares there. Now, of course, that only has 2 differences. It's a triangle with only 2 perpendicular sides, not 3. And lastly, from B to D, let's take a look at where B and D are. There it is there. Slightly awkward measurement. Halfway from B to the side, halfway back along the 12, and then all the way up to D is 4 more. And again, I add up those squares and take the square root, 8.25. All right, that's it. So we're doing distances. Now, some of you probably still have some things to get tidied up on 4A, but here's some questions here. Hopefully this won't take us too long. And there we are. So right now, this is our active section here. 4A hopefully would have been in by now, but if it's not, well, that's just the way it goes. And I'd like you to get 1, 2, 3, and 6 done from this current section, and we're going to see more soon on section C. Okay, well done.